So today we're going to talk about simulating employment, right? So we discussed already the kind of macro level impacts of the policy interventions that we modeled, road improvements and expansion of early childhood education. And so now we're going to talk about how we take one part of that and apply it to the micro level. Right? So we're going to look at employment changes, and we're going to actually select people who get these new jobs. Right? So that's basically what we're doing today. We're taking the jobs that we, the kind of bulk of jobs that we say will be created as a result of the macro portion, and then figure out who in the micro data is actually going to get these jobs. Right? So that's the challenge for today. And so again, if you haven't already downloaded the data sets for today, for today's exercises, please do so now. And also, have stayed already. So we're going to talk a little bit and then do the first exercise, talk a little bit more, do the second exercise, and so on. Right? I know the schedule says I'm going to talk for 40 minutes and then we're going to have another hour of exercises, but you don't want to listen to me talk for an hour. So I don't want to listen to me talk for an hour. Okay, so that being said, let us begin. So, so we're basically going to talk about the method we use to predict the changes in employment. And tomorrow we'll cover changes in time use and in time and consumption poverty. So I'll talk about the kind of broad outline of the process, and then we'll go through the different steps and do some exercises that kind of will show you how a little bit how the sausage is made, so to speak. Not too detailed. You should be able to go through the process without too much trouble. Okay, so let's do that. So the overview. So how do we assign employment? Well, first we start with the CGE output, right? So we have an output from the CGE that's a level of employment in the different sectors, right? And a level of employment by factor type, right? So we're going to convert that into a matrix of jobs first. And so we have the 9 sectors, right? Remember the capitalist own account sectors and the ECE sector and the public sector. So those 9 sectors, and then the different types of employment and the different labor categories, right? By rural and urban and the 4 education categories. So that's what we're going to do. So then we're going to identify donor and recipient pools. So what we're going to do is we're going to use the microdata that we have the synthetic data set that we created to estimate the time and consumption poverty measure for Ghana and Tanzania, respectively. And we're going to identify people in those data sets that might get the new jobs. And then we're going to pick existing jobs from within the data set to assign to those people. Right? So we're not taking jobs away from the people we're assigning from, but we're creating new jobs, but we're basing it on the existing structure of employment. Right? And so we'll see how that goes. But so the first step is identifying who are the recipients potentially and who are the donors. Right? And so the donors are going to be people who are working, right? And so in this particular application, we're assuming that the new jobs are in the paid employment sector, right? Okay. Okay. For recipients in Ghana, it's going to be those that are not currently working for pay, but in Tanzania, we needed to those not working, we needed to include everybody who was not working at all, right? different approaches because the needs for finding people to fill the jobs were different in both countries. So once we've got the donor and recipient pools set, for the recipients, since they're not already working for pay, we're going to figure out what the likeliest sector and occupation for each one is and the likelihood of their being employed, right? They're not employed, but we're going to have to figure out for each one, how likely are they to get a job if they were to go out, right? How likely are they to be the next person to go out and get that new job? Okay. So again, we're using the existing structure to figure out who's likeliest to get a job and what job they're most likely to get. Okay. And then we're going to go through a labor supply model that is going to give us imputed wages and hours, okay, for each recipient and each donor. Now, what we're going to use this for is to do the next step, which is, well, the next step is not that, but we're going to estimate each individual in the recipient pool's contributions to family farm income or family non-farm business income, or both, right? So since we may be drawing some people out of the family farm or the non-farm business, we have to see whether or not it's going to make sense for them to transition into paid employment. Okay. So we want some measure of what the trade-off is. Finally, we're going to assign jobs, and this is going to be done using a hot deck matching situation. So from the pool of donors, we're going to be picking people to assign jobs. So we're going to be picking people most like each recipient and taking their employment information, the hours, the earnings, and assigning it to the recipient. Okay, so we'll get into more into the details, including how we figure out how to pick the most like person there are in a bit. And then once that assignment is done, we compare the earnings from the assignment to their actual contributions, and we use a threshold to decide whether or not they're going to actually move into that job. And then we keep kind of cycling through until we assign all the jobs. Right? And then once we've assigned all the jobs, we're done. Okay, and so that basically means each time we kind of go through the loop and we subtract from the matrix of jobs that were created the number of jobs we've assigned until we're left with none in all the cells of that matrix. And then we can kind of look at the new the new distribution of employment, the new distribution of earnings and hours, and see if it makes sense. The thing with this kind of procedure is it's difficult to assess how good you've done, how well you've done the job, because you're creating a counterfactual distribution of employment and earnings. So you don't really have anything to compare it to. Right? So there are some things you can do to kind of make sure that things aren't too crazy, but that's about it. So we'll see. Okay, so that's the general outline that we're going to go through today in terms of the steps that we go through. And the data for the project, right, was a synthetic data set for Ghana that we created by matching the Ghana Living Standards Survey for 2012 and the time use information, the time use survey from 2009, right? So we did a statistical match of those two, and so we brought time use information from the time use survey into the Living Standards Survey to create this data set with which we could estimate the time and consumption poverty. That was the previous, that was phase one of the project. We're talking about phase two today. And so for Tanzania, a similar procedure was used to match the household budget survey from 2012 to the time use survey from the labor force survey in 2006. Okay, and then of course the CGE model for each country, which gives us the employment changes as a result of the policy interventions. And so we do 3 sets of these kind of employment assignments, right? One for the 3 different scenarios I talked about last time, the road improvements only, early childhood education sector only, or both, right? So those 3. So we do 3 scenarios of assignments, but the process is the same in each case, just the numbers of employment, number of jobs in different sectors change in each case, right? Okay, so that's what we're going to do today, basically. We're going to look at how that's done. Any questions before I move on? Okay. So let's allocate some jobs. And by this, I mean, what we're going to do for all the recipients is we're going to identify we're going to rank in the procedure we go through. We rank for each recipient, the likeliest to the least likely industry and the likeliest to the least likely occupation, okay, for that recipient. And that is going to give us a way to kind of exhaust all of the jobs in this matrix, right? So what we have here is, this is the overall jobs. I didn't break it out by types of employment, types of labor, so rural, urban, by education class, but for each of these are the changes in percent, right? These are the percentage changes in employment, and you can see, the roads employment. There's for the roads in Ghana, there's a variety. A lot of the changes about 3%, with construction being the largest, right? Since it's the focus of that intervention, right? So, public services being fairly small. For the care expansion, the care services sector is obviously going to see a huge increase in employment, 135%. And so everything else, not so much, because it's a fairly small intervention, and it's fairly labor intensive. If you put them both together, the combination looks kind of like adding things up. Now, Tanzania, similar situation, although the impacts on employment are generally smaller, except for care, which is a little larger than in Ghana. Okay. So these are the changes that we're going to try to model, that we do model in our simulation. Now, how do we go through about that? How do we go about doing that? For the donor and recipient records, we have to identify who's in which group. And so for donors, we have employed people in income generating activities, aged 15 to 70 years old, right? Recipients are all eligible individuals, so eligible to receive. They're not already working for pay. They're aged 15 to 70 years old. They're not retired, not in school, not disabled. Okay. So, so we identify those for each country, and then we can go ahead with the next piece. Now, for different kinds of simulations, the donor and recipient pool are going to be different, right? But for this specific application, this is what we use. Okay. Okay. Now, what you'll typically find in a situation like this, where we're trying to simulate employment, is that the donor and recipient pool are going to be very different. And so the blue bars are recipients and the orange bars are donors. So you can see that recipients tend to be younger, right? And, excuse me, more likely to be female in both countries than male, than donors, right? And you notice that the donors kind of peak in the working age sector, the working age range for both countries. But at the lower levels of the younger, the younger you are, the more likely you are to be a recipient, male, female, Tanzania or Ghana. Right? So because we're taking this from the actual situation, the people who aren't working are the ones who are less likely to be working, right? It's kind of the way it is. So they're different. That's the point. Right? And so that's going to come in when we impute hours and wages for these people. We have to use a method that corrects for sample selection bias, right? And so that's what we're going to do in the second exercise. We're going to talk about that. But for right now, how do we then figure out for each person, what the likeliest industry, what the likelihood of being employed is? Well, we use a statistical method to kind of figure out what the patterns are in the actual data, right? So for the SAM aggregates and occupations, we use a multinomial probit on employed individuals, and then we predict, use that model to predict for recipients what likelihood it is for each of them to be in each of the aggregate industries and occupations. Okay. For the likelihood of being employed, we use a probit on donors and recipients, right? And we predict for the recipients the likelihood that they're being employed. So we do this because when we're going through each combination of SAM aggregate industry and labor type, we pick the people who are likeliest to be employed first, right, as recipients. So all the recipients aren't going to get jobs because there are more recipients typically than there are jobs to give in these scenarios. So we have to, use something to kind of decide who's going to get the job and who isn't. And so we use this likelihood of being employed generated this way. Okay. And then for hours and wages, which we're going to do in a bit, we use a three-stage Hecate, right? So it's a labor supply model where we first test for sample selection into the labor force, the employment probit. Myra, do you mean?
Yes, I mean the employment. Is it all together, the probit, and then you assign the sector, or you do a probit for each sector?
Yeah, what we do is we generally do the probit by sex and age categories, and then use the sector and occupation as explanatory variables, right? So what we'll do is use the most likely predicted sector and occupation for the prediction of employment, or leave it out. But it is definitely, we do it for the whole pool of recipients, divided up by sex and age. Right. Okay, so now we're ready. Unless there are other questions about what I just talked about, we can do the first exercise. We're ready. Okay, so let's fire up Stata if you haven't already. I hope you have. Okay. All right. Oh.
I have a quick question, if I can.
Yes, Anna-Marie.
It's just more like a more, I think, conceptual. So the idea of donor is that the policy implementation will generate new jobs, right?
Right.
But that doesn't mean that those who are unemployed are going to be the better fit for those new job creation. So we are kind of assuming that there is going to be a reallocation of the overall amount of employment that would be after the policy. And that's why we need that donor recipient kind of match.
Well, no matter how you approach it, you need donors because you have to have some kind of job right, characteristics to assign to to people who are receiving jobs, right? In this case, we did not reassign everybody, right? For people who were already employed, we left them employed, right? But for the jobs that were created, we took people who weren't already employed for pay and put them in those positions. Right.
Okay, so
But to-
just to confirm, we are not going to one who is already employed we are assuming that it's not going to change and take one of those new jobs, and then one or those who are unemployed are going to take the old job. That's some sort of
Right, right. No,
Okay.
what we're doing is, the assumption is that the new jobs that are created are going to look like the already existing jobs, right? So we want to take an actually existing job, you know, with hours and earnings and sector and occupation, and assign it to a new person, right? We're not taking it away from the old one, right? We're just, yeah. So there is an implicit assumption that the new jobs are the same, or not necessarily worse off, but the point is that the new jobs look like jobs that are already existing. Right? So you know, that's a limitation of this kind of simulation when you're using this kind of data, right? Is you can't well, we're not kind of simulating a new and wonderful future in which people are paid more, right, and have, you know, decent working hours and all that kind of stuff. We're taking the labor market as given, and you know, figuring out what is the likeliest job that each person who's getting a job would get, given the current situation in the labor market. Okay, so you have stayed open, so you can open up the day 11 data set. Okay, and so go ahead and create dummy variables for donor and recipient. Remember, donors, we'll assume that donors are going to be people working for pay between the ages of 15 and 70. Right? And there is a variable in there called empstat. If you're not familiar with the codebook exam command, I'm gonna stop sharing for a second and share this screen. Okay, so a useful tool in Stata when you're first using a new data set is the codebook command. Right. So this tells you a lot about the variable that you pick. You can also do it, just codebook will give you this for every variable. But for now, we can just look at employment status. You can notice here there's a category with a value 1 that's paid employment, right? So these are going to be the donors. Another useful function that you can use is in range. And this returns a 1 if the variable z is between a and b inclusive, right? So this is useful if you want to pick people aged 15 to 70, right? So how are we all doing? Put your head down on your desk if you're done. Done. Nice, Deborah. Deborah gets an A for the day. Good, good. Okay. So here's what I do. Right. We have we already have dummy variables for people who are disabled, in school, and retired. And then I use this in range. So I create a variable called eligible. Then I create the donors who, as I said, they have employment status of 1 and they're between 15 and 70. Recipients are, not disabled, not retired, not in school, between 15 and 70. They're not donors, right? And also use AGPOR, which is the time-adjusted poverty indicator, right? So the recipients look like that. Okay, so now that's what I get. So I have 275 donors, 690 recipients potentially. Okay. By the way, after this class, I will be posting my solutions to my problems. So if you're wondering how I got this, let's see. This and the donors and recipients is fairly standard. The rest of the stuff we're going to do is a bit simplified from what we generally do, but you can see the general idea. Okay. So next. Oh, for Pete's sake, what's going on? Okay, so now we can run a probe it on employment for all adults. Okay. Let me go back to the assignment. Oh, I'm just going to share screen too, since that's where all the good stuff is. Okay, so we've done this. Now we're gonna run a probate unemployment for all the adults, so 15 to 70. We're gonna call those adults in this situation. And then we're gonna predict for all the recipients. So we use the probate command, which you may or may not have used before. It's a maximum likelihood estimation, right? So we need to create a dummy for employment, and then use the probate command on that using variables that make sense, we hope, right? And then once we've run the probate command, we use the predict post estimation command with the PR option, which will create a new variable with the predicted probability of being employed. Okay, so let's take a look. So to create a new entrant, welcome. So to create a dummy variable for employment, use the labor force status variable. You'll notice that one value has employed, another has unemployed, and one has not in labor force. This, by the way, is a nice way to create a dummy variable, right? I'm using the generate command. I'm giving a new name to this new variable. I'm just calling it EMP, and I'm assigning it the result of this expression, right? So I'm comparing this variable to 1, right? So in other words, this double equal sign is a comparison. So if LFS is 1, this returns 1. If it's not 1, it returns 0. Okay, so in other words, if LFS, this labor force status variable, is 1, employed, EMP is 1. If not, it's 0. Right? So that's useful. Okay. Has anybody run the probate yet? Does anybody have some results they would like to share? Nobody's feeling brave. Anyone? No? Is anyone having difficulty? Okay, well, based on your responses, you're all done, and none of you had any difficulty. That's great. So Daniel, you want to show me what you did? share your screen. I'm picking on Daniel because he was my student at the Levy MS program, so he'd better know this.
I'm still working on it, of figuring out what the weight variable is called. Also, I don't have a second screen.
I see.
I can share my results.
Great. The weight variable is called WGT.
Oh, I didn't wait it.
Well, I'll allow it this time, but you should use weights. But
I'm not sure, confident about the results, but I use a probit of employment to age, sex, household head,
okay,
number.
Myra, your Zoom screen is on top of your Stata. So if you could just share your Stata window, maybe.
There?
No, still.
How strange. Oh, there I can see it.
Oh, okay. All right, go. It must be me then.
Maybe I can.
Oh, okay. That's never mind. I'm just being a dummy. Don't worry about me. That was my own Zoom screen that I was seeing in front of yours. Okay, great. So you have you've used age, sex,
Household head, a number of kids in different age ranges. I've used education as dummies, and I only use it for the adults.
right.
So here are the results. The iteration went really fast. And I don't know what I if you want me to comment on the results or just.
Well, yeah, we don't have to worry about, the coefficients or any of that stuff, right? But one thing I will note is that you definitely want to be careful if you do a code book of the sex variable. See, that's not an indicator variable, and so because it takes the values of 1 and 2, right? The probit will treat it as okay. You can just use the I dot notation with a categorical variable like that as well, right? So
I can run it again.
yeah. Oops.
Something got next.
Okay. There you go. Okay. So we have results, right? The pseudo R squared is 0.1296. It's not terrible, but it is what it is. It's enough. You can play when you're actually doing this. You can play with the model that you're using, but once you've got the results, we can now predict the likelihood, right? So we can use the predict command, and you can go ahead and stop sharing.
Thanks.
And I will go back to sharing my screen. And so, yeah, so, God, what's this? All right. Okay. So here's what I used for mine. And I didn't even weight it mine, which is a no, really. But so I used a few more things. I got a little more out of it. But what I'm going to do now is predict, not reduct. And so I'm going to give it a variable name, and I'm going to use PREMP, so predicted employment, with the PR option, which gives me the probability. With the use FW frequency weight with the WGTI is integer weights, and definitely use FW, which is the frequency weight option for that. Right. So. Okay, and so you can see that what I get ranges between 0.36 and 0.97. Right? So this person here is the most likely to be employed, and these are not, less likely to be employed. Right? And if I do this by donor, this by sort variable name or variable list colon will do whatever you say by categories that you specify here, right? So for these we don't need to worry. But so the recipients, right? We have a range of 0.36 to 0.97. For the donors, a little higher, right? Not a lot higher, but the average is actually lower. That's weird. Okay. So once we've done that, we can go ahead and do a multinomial probit of industry. Okay. Now, since it's almost 10 of, I'm going to say let's skip that, and you can take a look at what I did in afterwards in my program here. Okay. But for now, we're going to go back to the last step here is important though. One good practice when you're doing analysis with Stata is once you've done some things that you want to keep, save in a new file, right? Don't overwrite the old file because you want to keep the original data so that you can repeat what you did, right? So it's just a little bit of standard good practice. And you can save with the save command. Right. Okay. Where's my Zoom window? Oh, here we go. Okay. That's a good one, Daniel. I'm just looking at the chat. Well done. Daniel paid attention in class. It's good. Okay, so that's the general how we go about assigning the likelihood of employment, the likelihood of industry, right? The mprobit is a multinomial probit command. So it takes what it does is it takes a categorical variable rather than a dummy variable, right? And it will generate for each value of the categorical variable, it will run the model and give you a assigned probability for each category, right? And so then you can predict the likelihood of each category in a set of variables afterwards, right? And you'll see how I did it in my code that I'll post. Okay, so let's talk about imputing wages and hours. This is a multi-stage generalized Tobit procedure. So the idea is you want to impute wages for people who aren't working, right? You can't just run a regression of wages on people who are working and then predict using those for the people who aren't working. because you know, the people who are working, if you run a wage regression on those people, you have a sample selection bias, right? Because the people who are working are different from the people who are not working, you know, in important characteristics that actually affect wages, right? So if you want to predict wages for people who aren't working, you have to correct for that, right? So that's what the Heckman procedure does, right? So this is pioneered by James Heckman, econometrician. So the first thing you want to do is estimate the likelihood of being in the labor force. So basically, you're testing for selection into the labor force, right? And next, so that's, you run a probit on labor force participation for all working age adults, right? So for everyone. So it would look something like this. There's a vector of characteristics X, right? There's a constant and an error term, right? And so it's a little more complicated than this because it's a maximum likelihood estimation. You're using the probability density function, but you know, that's the general idea. What you then do is predict labor force participation for all working age adults using the results, right? So just like we did for employment just now. But what you take this and then figure out the inverse Mills ratio, or lambda, we'll call it, which is this lovely little thing. Sigma underscore LF is the standard deviation of this prediction. Okay, and so you take the probability density function of the prediction divided by its standard deviation and divide by 1 minus the cumulative density function of the prediction divided by the standard deviation, right? And that gives you lambda, which you can use to correct for sample selection bias, right? So what we're doing is we're explaining the selection, right? And we're using that selection, right? That prediction of selection here. And we're going to take this and use it in the wage regression to correct for the sample selection bias. Okay. Now, you can do all this by hand, but there's a static command, Heckman, that will do it for you. And we'll show you how that works. Then you predict the wages based on the OLS regression, right? Use a log because wages are not distributed normally, generally speaking. And so we use a different vector, right, of explanatory variables for wages. This has to be different. We can't use the same, all of the same variables in the selection regression that we use, and then use them all in the wage regression, because you have to be able to actually account for the selection. And if you use the same variables as in the wage regression, you can't, right? So typically, it doesn't take a lot of imagination to think of variables that would affect participation in the labor force, but not wages, right? So, and in the data set I gave you, there are variables that will affect labor force participation, but not wages, right? And if you look, you can probably pick some of the ones that I mean. But technically, you need to have at least one variable in the selection equation, right, for labor force participation that is not in the wage equation, right? Otherwise, lambda is just a combination of these, and you can get multi-correlation problems as well, right? Okay, so now we can predict the wage, right, using the assigned industry and occupation for each recipient and the actual for the donor, right? So in the previous step, we would have picked the most likely industry and occupation for each participant, for each recipient, and we would use that to predict their wage, right? Along with the inverse Mills ratio, which is the sample selection bias correction. So we can use that imputed wage in the next step, okay? Because we don't just want to figure out wages, we also want to figure out hours, right? So we predict hours based on the OLS regression. We use the imputed wage that we just created and the inverse Mills ratio, right? So we have a second set of characteristics. Maybe they're the same as the first, maybe not. Most likely they're going to be the same. But we also include the imputed wage, right, which we're implicitly assuming goes into the decision about hours, right, between the employer and the employee, and the correction for sample selection. And then we predict the wage. Oh, this should say hours, sorry. Using, somebody was using copy and paste. I think it was me. And so now we use the results of this to predict hours. And now we have imputed hours and earnings, right? Those we're going to use in the matching, right? We're going to use those two created variables to match donors with recipients, right? In the last step. Okay. Okay. That's the general idea of the Heckman three-stage process here, right? So you predict the likelihood of being in the labor force. Myra, I just saw your hand. Yes.
It's just one question that I got I didn't understand. Do you impute for all the donors and recipients, or only for the ones who are not currently working?
We impute for both donors and recipients. Right.
So then in the baseline, you are comparing, when you compare the baseline with the contrafactual, do you have differences in those who are already working, or the baseline is also imputed?
Well, just to understand what you're asking, the wages that we're imputing and the hours that we're imputing are not going to be the ones we're assigning as the new jobs, right? We're creating these to do the matching with, right? Then once we do the matching, we're going to carry over the actual wages and hours from the jobs that we're assigning, from the donor that we're assigning to the recipient, right? So these are kind of intermediate steps to give us more information about who's like who in terms of employment.
I understand. Thank you.
Okay. Yeah. And then Ming Tam. Okay, Ming Tam asked about weights. So the integer weights I generally create from the weights that are given with a data set if they're not integer weights, just by using the round function. But if it depends on what kind of weights are in the data set. In this case, they're not probability weights, right? They're the inverse of probability weights. And so I would use AW for the raw weights in the data set, the WGT variable that's not an integer, right? So not PW. Probability weights are generally between 0 and 1, right? Okay. Okay. So any other questions? Now we're all labor force supply specialists, all you macroeconomists. See all these things you don't have to worry about when you're a macro person. Okay, so let's do it. Let's run a Heckman. So like I said, Stata gives you a Heckman command, right? And it's called Heckman, right? And so so you supply a function. So this would be the wage function. So log wage with whatever variables you want to use to explain wage, variations in wage. And then the selection function here. So this would be the labor force participation variable, right, is equal to some other set. So you can use x1, all the x's if you want, but also at least one other variable, right? And there are at least two that I would use if I were you. Hint. And then this mills, right? Whatever you provide here is the name for the variable this command will create, which includes the inverse, which is the inverse mills ratio, right? So you want to create a new, you want to use this option, so you have that available for the hours command. This, the result of this will give you predicted wages, but you'll have to use this, whatever name you give it, lambda, say, in the hours OLS. Okay. So go ahead and run a Heckman command. So, and be sure to use weights. Go ahead, use frequency weights. That'd be great. But before to include this, be sure to include the select option with a selection equation. Right. And the mills option with a variable name for the inverse mills ratio that you want to use. Oh. I sent that to Professor Floro instead of everyone. Questions? Is everything going smoothly for everyone? Okay, so who wants to show me what they got? No one, huh? Okay. So how about Erica? Can you show us what you have?
Sorry, I got stuck in the first phase, so not able.
No? Okay. Who else? Who can show me? That should work.
Then I can show you.
Okay, go ahead, Daniel.
Yeah, I think this is what I got. Not entirely sure how to read this, but
Okay, well, this functions, right? You got results, which is nice, right? It's fine. So you have the first panel here, which is the wage equation, which will include the correction, right? The second part here is the selection equation, right? And then at the bottom, you see the estimates for lambda, right? So this is a good example of a working Heckman command, right? So I'm going to go ahead and good job. Don't entirely don't congratulate yourself too much yet, because it's not the model I would use. Just saying.
I wasn't sure which two variables you meant.
Which two?
You hinted before that there are two variables that
Oh.
affect labor force, but not the wage, right?
Yeah. Well, there are at least, right? So marital status, right? I would think of as oh, let me finish sharing. So at least a couple, right? Marital status, right? I can think of that as affecting labor force participation, but not necessarily the wage, right? Although, you know, it all depends on how gender discrimination in the workforce happens, right? But the number of children aged 0 to 5 and 6 to 17 would have a significant impact on labor force participation rates, especially for women, right? But maybe also for men, the other direction, right? So those are the ones I would think of most directly, but also maybe the household head, right? So curious on the marital status. Yeah, that's, it's an open question. So let's see what I got with my. So now let me first create the log of wage. So here is my command, right? So I use education, region, rural or urban, sex, age, number of kids under 5, number of kids 6 to 17, and marital status in the selection equation, right? And then, oh, I need to use, this command, this function here, right? Enlist is another nice one to use when you're creating variables. It tests labor force. If LFS, that variable, labor force status, is 1 or 2, or any other commands, any other values I put in here, right, separated by commas, it will return 1. If it's none of those, it'll return 0. So LFPR So here's what I get, right? So employed, unemployed, LPR is 1, not in labor force, 0. Okay. And so that's what I'm going to use. So here's what I get. Okay, so education, industry, right, rural, urban, central, the region, female, age. So I used all of those to try and explain wages. For labor force participation, I used education, urban, rural area, sex, age, number of kids under 5 and 6 to 17, marital status. So right, so married is the one missing here. Everything else has a lower probability of being employed, see, right? So yeah, so that's what I got anyway, Lucy, to respond to your question. And then, so now we can take a look at lambda. Right, so now we have values for lambda that we can use in the next stage. And we can go on from there. Now, what I'm going to do, let me use my, where am I? There we go. Since I already did this, I think, I hope. Damn. Okay. So I didn't do this, but what I would do next is use the likeliest industry, right? So a variable I created up here as a result of the multinomial probit. So I predict a vector of variables for each industry, the probability for each one, and then I figure out for each individual what is the maximum probability using Romax. Okay, so for each individual, then it'll look at all of these variables and return the largest value, the greatest probability, in other words. And then I replace Lind with that industry if that industry's probability is equal to the maximum for each individual, right? So I create a variable with the likeliest industry, and that's what I call LIND. And for the recipients, I would replace IND1, which will be empty, with the likeliest industry to do the prediction of wages there. Okay. And then I use that and lambda in the estimation of hours, right? And then I can predict hours as well. Okay, so that's the general idea, right? A quick and dirty introduction to a labor force supply model for you. Any quick questions? Okay. Any questions I didn't answer in the? Okay. So any surprises about this? The effect of marital status on labor force participation rates. Well, I should say that this is, a kind of a subset of the Ghanaian data that I'm using here, right? So I just picked about 10% of the households from the Ghanaian synthetic data set for Ghana, just so it'll be a little smaller and easier to use, quicker. So I wouldn't necessarily say that these are the actual results you would get, but it is what it is. But pretty much all of the married women are likelier to be in the labor force than everybody else. And married, this includes men, of course, right? Women are less likely, but married people are more likely. If you want to get technical, you can start to do some some interaction terms, like with sex and marital status, for example, right? That might give you a little more detail, but it is what it is. We don't have to be exact here. This is just kind of to show you how it works, right? Not to produce a publishable paper or anything. Okay, well, we're already past our break time, so let's take a break now. And then we'll come back and carry on. So if you have any questions that come up while you're taking a quick 15-minute break, you can bring them back, and then we'll go along. Yeah, sex and children would also be appropriate, for sure. Okay, so see you back at 32 past. So now that we're all labor force experts, okay. Well, I'll see if I can figure out the in-range question, but for now, let's move on to estimating contributions. Now, this is basic. The point of this exercise is to when we've made the assignment, to have something to compare to. So when we make an assignment of a new job to somebody, the question is, will it be worth it for them to actually take the new job, right? So we're saying this job is available to them, but if their contributions to household income are, much greater than that new job, it wouldn't make sense for them to stop working on the farm or the non-farm business and work in this new job, right? So we have to come up with some test, and what we do is we estimate individual contributions. So what we're going to do then is for each household, right? We're going to generate for the farm and the non-farm business separately the number of hours devoted by family members to that farm or non-farm business, right? By age, gender category. And then we'll estimate an OLS, a regression of a log normal production function, right? So that looks like this. So the log of income is a function of the log of, this is a vector of the age, gender category, labor inputs. And then X is other inputs, right? And Z is a vector of household characteristics that might affect it, region, agroecological zone, etc. And then an error term, okay? And so this, we estimate this at the household level. These are all household level variables, right? This vector of variables aggregates all the individual contributions to the household farm or non-farm business, right, in terms of labor hours. So what we're trying to do with this is use the results of this to figure out what each individual actually contributes, right? So what we do then is we predict household farm or non-farm income. So again, we do it separately. And we get the ratio of the inputs to family work hours. Okay. So the point here is what we're going to do is we're going to predict household farm or non-farm income without the without each individual's inputs into the farm or non-farm business. Okay, and see what happens to output. So what we're going to do is we're going to reduce the number of inputs as well. So we're going to say that if we reduce the number of, if we reduce the amount of family labor, we're going to reduce the amount of inputs at the same time. Okay, now we predict incomes without each individual's worker's labor and less the associated inputs. Right? So we figure out if we reduce, by this person's amount of labor and the associated inputs, what would the income be? And then the difference is the net contribution for each individual. Now, what we then do is we take all of those net contributions and scale them so that they add up to the net farm and non-farm income for the household. Right? So what we have when we're done is for each person that provides family labor to the farm or non-farm enterprise, we have their share of the income that's generated, right? So we figured out for each person what portion of the income they generate, right? Their inputs provide. So it's a proxy really for figuring out, the cost benefits of taking a new job, right? The benefit is the new earnings, but the cost is the reduced household income from farm or non-farm business. Right? So that's what we're estimating here. Is that fairly clear? Clear? Okay. Well, so I was going to have you do this, but the two exercises in the first part of the class today took a little longer than I expected. So I'm going to skip this exercise, although you can do this for homework, right? Of course, I did share the file with you of my solutions, so that can guide you as you go through. This exercise is kind of a simplified version of what we actually do. There's a little less detail in my file than the actual process, just to give you a flavor of what it would be. If there are any questions, we can talk about them. Okay. So finally, we're ready to do the actual match. And this is the kind of most time-consuming and involved part of the process, the actual assigning jobs, right? So what we need to do is we end up dividing the data set into subsets by age category and sex of the individual. So what this means is that once we start to do the matching, we're only matching women with women and men with men, and we're matching people of similar age categories. Okay, so not the same age necessarily, but close, within 10 years or so. So we use the imputed industry, occupation, wages, and hours for the recipients, and the actual characteristics for donors, although we use the imputed wages and hours, right? We use the actual industry and occupation for the donors. And we generate what's called an affinity score, right? Which is a weighted sum of matches between each recipient and all of the donors for a set of matching variables, right? So I'll talk about this in a moment, what this actually means. But from among those with the highest score, right? So this score basically is a measure of how similar records are to each recipient. Right? So for each recipient, we generate an affinity score for all the possible donors. And then, so those scores are going to range from 0 to whatever. And we pick all of the donors with the highest score, right? So however many that is. And so from that set of subset, right? Okay, Pravina, you shared that with me. Okay, there you go. Thank you. From the subset with the highest score, we pick randomly, right? Now you can do this more than once if you want to create multiple imputations to get kind of a little bit of stochastic factor in there, but you know, at least once, right? So you want to pick at least one donor. And then what we assign the donor's sector, occupation, earnings, and hours of work to the recipient, right? So that job that the donor has, we're saying that the recipient gets that exact same job, right? So we're basically taking jobs that exist and replicating them for the recipients of the new jobs. Okay. But we're not done, because we're going to now compare the new earnings to the estimated contribution of that individual recipient, right, to their household farm income or non-farm income or both. Okay. And if it's below 75% of that contribution, we say no deal, right? So that person does not get that new job, right? They won't take it because it's not, it doesn't pay enough to get them to move from what they're doing in the household farm or non-farm business to the new paid job. Okay. But if they do get the new job, then we subtract that recipient's weight from the number of jobs in the matrix corresponding to the sector and the recipient's rural, urban area, and educational attainment, right? So that eight category labor, right? And the 9 aggregate sectors, right? That's the matrix of jobs that we have. So that's how we keep track of how many jobs we're actually assigning, right? We don't use, we use the survey weight, right? Because the CGE output is the total for the whole country, but the survey data we're using is representative, so we have to use the weight, right? Okay, so now that's what we do, though, is we kind of do these multiple nested loops, right, through aggregate sectors and types of labor. And then we're doing it by first everybody's most likely industry and occupation, right? And once we've done all the matches we can with every recipient's most likely industry and occupation, we go to the second most likely industry and occupation and do it all again. And we keep doing that until we're all done handing out the jobs that were created. Right? So it's loops within loops within loops until we hand out all the jobs, right? But within each loop, we do this. This process is the same. So, you know, don't worry too much about the loops for now, but that's the idea. We hand out jobs based on the nearness of each donor to the recipient. Okay, so that's the general outline of the assignment that we do, the matching. Okay, so let's talk a bit about this affinity score. So the affinity score is a way to capture how like one observation is to another, right, in important ways. In this case, because we're assigning jobs, we want to use characteristics that determine the kinds of jobs that you would likely get, right? This is why we used the Heckman procedure to impute wages and hours, right? This is why we predicted the likelihood of being in a specific industry and occupation, right? So, so what we do is for each recipient, right, we take all the donors and calculate the affinity score right? So we compare each donor to that recipient using a set of characteristics, variables in the survey. Right? And so the simplest is just like this, right? So it's a sum of matches, right? So this one is an indicator function, right? So if this is true, the value is 1. If this is not true, the value is 0, right? So basically we're saying x0j is the value of the jth variable for the recipient observation, right? So if we have p variables, right, the number of matching variables, for each one, we compare the each donor's value of that to the recipient's value for that characteristic. And for every match, you add 1. And so alpha can go between 0 and p for each donor. Okay, so so alpha is a measure of how many matches in terms of characteristics there are between each donor and the recipient. Okay. So then once we do that, we can use that set of observations as the nearest neighbors for each observation, and then we can draw randomly with replacement, right? If you want to do multiple imputations, you do this more than once, right? So we calculate alpha for all the donors. The maximum value of alpha is the set of nearest neighbors. And so we use all the donors with that value of alpha, and we pick randomly from that set of donors, right? So that's the set of donors who are most like the recipient. And we repeat that for each recipient. Okay. Now, there are a couple of complications. First, this works really well for categorical variables, right? So industry, occupation, but what about imputed wage, right? The wage can vary a lot. So are we going to say this is 0 even if it's very close? No, right? We don't want to do that. We want to use something else for continuous variables, right? And so we'll use a distance. So we'll say if it's close enough, then it's a match for continuous variables. Categorical variables like industry, education category, right? Those have to be exact matches. But continuous variable like imputed wages, imputed hours have to be just close enough, right? And so, you know, a good range is say 1/2 of the standard deviation of that characteristic, that continuous variable. But you can play with that, right? The larger that range is, the more matches you'll get, and so you'll have more people to pick from. But then you'll also get people with that are less and less similar to the recipients, right? But you can kind of play with that as you go. So now what this looks like is alpha is a function of x and z, where x's are the categorical variables. So this is the same as before. We have j categorical variables and k continuous variables, where the distance here is less than 1/2 times, that looks like 1/2. I'm sorry. This should be 1/2 times the standard deviation for that variable. Okay. I gotta fix that. Not to worry, tonight's session will get the correct one. So they get the benefit of my mistakes that you have to live through. Okay. So great. Is that clear? So we want to use a different criteria for continuous variables. That's the point, right? We don't want to use an exact match for the imputed wage, right? Because that's going to vary a lot. Okay. One more modification is the idea that you can use weights, right? So implicitly, we're going to treat treats all of the variables equally, right? but it may be that you want to prioritize some variables over others, right? So some variables may be more important than others. So we can give more weight to some characteristics than others. Okay, and so you can replace the implicit weight of one with your own weights. So now we have this kind of full definition of the affinity score, where we have weights for each variable that you can specify. And so now the alpha doesn't just go from 0 to j plus k, right? It depends on the size of the weights, right? And so depending on how you want to use the weights, you can specify just how much each thing matters. So you can give a really large weight to one variable that you definitely want to get right. Yeah. And smaller weights to other ones. So is that clear what we're doing with the affinity score here? Right. So there are things that you can play with, the weights and the the scale, the range that you choose for continuous variables, as well as the actual variables x and z that you choose to use in the matching, to basically come up with the set of donors that are most like each recipient, and so that you can choose at random from that set. Okay. Okay. So I have a program that I wrote called MIHD that kind of does this, and I'll share that with you afterwards. But just to give you a sense of how this looks, right? Once you're all done doing the matching, we can try to assess quality of the match, right? So what we're seeing here is the ratio of recipient to donor earnings by sex and education, right? For median hours, median earnings, mean hours, and mean earnings, right? So if how worried are we by the fact that everything isn't at 100%? You may remember I mentioned it's hard to assess the quality of a match like this because what we're doing is creating a counterfactual distribution, right? So, how worried should we be that the earnings for women in Tanzania who have completed primary education are 250%, 2.5 times among the recipients compared to donors? Well, it's hard to say, right? Should we be worried by that? Maybe if it was 1,000 times, I would be more worried. Right? But the main point is the fact that the recipients, in terms of these categories, are very different from the donors, right? So recipients in Tanzania tend to be female. They tend to have lower levels of education, and for those, the hours are pretty close, right? The earnings though are kind of lower, right? So that's a problem. But it's impossible to say how big a problem that is. The main point is, are the results plausible? You would think they are, since we're basing it on the actual existing characteristics. Okay, so I just saw Erica's hand. So yes.
Okay. Sorry, this is a question about the previous slide. I am familiar with having a weight for observation, not with using weights for variables. I don't know, maybe this is a silly, simple question for the other people in the group. So I don't know whether you want to use some time for explaining just very briefly how one gives weight to variables.
Sure. So an example of this would be for this specific application, right? So I'm trying to assign jobs. So I'm using the industry for donors and the imputed, likeliest industry for the recipients, right? So for that, I would assign a really high weight to that variable. So I want to get that one right for sure. So I'll make that one, give that one a weight of 1,000. So for every donor with the same industry as the likeliest industry for the recipient, the affinity score would go up by 1,000, right? And so that would basically filter out everybody that doesn't have the same industry, right? So that's kind of a drastic example. But if you, depending on how the match works, how the pools are, how big the recipient and donor pools are that you're working with, you might want to separate it out that way. There could be other examples, of things that you definitely want to get right, like rural versus urban, for example, right? You might want to give that a really high weight, and then give things like, the number of kids or marital status or something like that, lower weights. You want to get them, you'd like to get them right, but if not, it's not as big a deal as getting the industry right. Do you know what I mean? So, for all of the donors with the same industry, they get 1,000 plus whatever other matches there are, right? Does that clear it up?
Yeah, thank you.
Yeah. Okay. Louisa?
Yeah, this also might be a stupid question, but so in the back of the algorithm here is every single possible recipient being matched with every single donor to calculate the affinity score of each one of those, and then you take the highest?
Yeah, we go through we go through the recipients one at a time and create affinity scores for all the donors, right? Because you have to compare each donor to the recipient. Then we pick the subset with the highest affinity score and draw it random from that subset.
Is that runs quickly? It's not crazy.
Well,
I would assume the time to run this grows exponentially with the amount of observations you have, or no?
Yeah, sure. The program I wrote uses Meta, which is a matrix algebra component of Stata, which is a whole, kind of Stata squared. But that reduces the amount of time, right? If you just wrote this by looping through observations in Stata, it would take weeks to do a match, depending on, the size of the data set that you're using. But Meta makes it happen a little quicker. It still takes a while, right? For Ghana and Tanzania, they're pretty large data sets. And so the program to assign, those loops among going through all the different components of the matrix of jobs that were created, and then among all the age and sex categories, and yeah, it takes a while, but the program I wrote just to do the matching took hours to run. So so Myra has a question. Do you check if your donors are different, if you have enough variability? You can, and I built in some measures of, how many donors you're choosing from, right? So And so you can look at that and then play with, things like the weights you assign and the range of continuous variable you use to make a match, right? But there's a trade-off for sure. But frequently the pool of match variables is fairly small because once you start to filter out people that aren't like the individual with survey data, the smaller the subset that you're trying to match within, the fewer nearest neighbors you're going to be able to find. So. And also, like I said, implicitly, because of the way labor markets work, the people who are recipients are dissimilar from the donors, right? Because that's just the way it is. Right? Okay. So any other questions before I talk a little bit more about assessing it? Okay.
There's another one in the chat.
There is. Oh, okay. Well, every recipient, right, gets matched with a donor. Not everybody in the data set, but every recipient that we identified, right? Until we run out of jobs to assign. Yeah. So, okay. So so this is the mean and median hours of household production. Oh, this is a, never mind. Ignore that slide. You were not meant to see that. Okay, we only have 10 minutes left, so we're really not going to have time to do this. But what you can do is kind of work through the other, the first 3 exercises. And then you can figure out what matching variables you want to use, right? And what you can do is sort. You can use the sort command. So I'm going to say that the most important things are these aren't necessarily it, but I'm just going to say that these are for now, right? And then rural, urban, and then sex, and then, all right. So I want to say that these are my matching variables, right? So what I'm doing is kind of a rough and dirty a way to show you what matches might look like. Okay, and so now I'm going to browse. BR is short for browse, right? But I'll just write it out. So I'm going to include wage. Yeah. Okay. So I'm just going, so I've sorted, right? And now you can see here are the recipients, right? And here are donors. Here's a donor. Okay. So this is not a very, finely chosen set of nearest neighbors, right? So there are a lot of married men in the rural areas who have never attended school, right? In this data set. So some of them are recipients. Oh, what I should do is so I'm only going to pick donors and recipients now, right? So we have all these recipients, and we only have one donor here, right? But if these 4 variables were all I used for the affinity score, right? These would this donor and do we have another one? Oh man, this donor, right? And this donor would all be in the pool to match all of these recipients. Right? See what I mean? And so then they would get this wage and these hours, right? 119 hours a week. Ouch. That's kind of an outlier, but 84. You can see people work a long time, right? This was only 12. This is a donor, 7 hours. So this can give you an idea, right? If you start to use a few more, right? And if you go through the first 3 exercises and use the imputed wage, the likeliest industry, etc., you can start to see a little bit more how they, how the donors and recipients kind of match, right? And what are the possible donors for each recipient? Yeah. So it's hot decking, right? So what that means is we draw with replacement. So it's not what we call a constrained statistical match, where you can only match one observation once. Right? A single donor can be matched multiple times. Right? So we're not trying to reproduce a distribution. We're creating a new counterfactual distribution of employment and hours. So it can certainly happen that a single donor might be matched multiple times to a recipient. Okay. So questions, comments? So this is the whole kind of process, right, that we've kind of looked through in a simplified way. So we've identified the donors and recipients. For the recipients, we've identified how likely they are to be employed, how likely they are to be employed in specific industries and occupations, how what is the likely wage and hours that we get, and we can compare those between the donors and recipients, right? And so once we've got all that information, we can use that information to find matches among people who are already working and assign those jobs to the recipients, and compare that to the contributions they make to household income by working, doing unpaid work in the family farm or non-farm business, right? So that's the general procedure for doing the employment simulation, right? So simulating employment. For this case, we use up weights because we have a set of jobs that are newly created. You can also do a simulation where every possible recipient gets the most likely job and see what that would look like. We do that for in most cases when we do LIMTCP estatements. We also do an employment simulation for poor households to see what would happen if the adults who are not working for pay in those households got the paid job they're most likely to get, right? It's another kind of simulation than this one, where there's not. In this case, we have a set of jobs that we're trying to assign. Excuse me. So that's that. So what we're now ready to do tomorrow, quickly, is reassign household production time, right? because as a result of changes in the distribution of employment within households, we're going to see a shifting in distribution of household production time as well, right? So we're going to go through a similar process to simulate that new distribution of household production time. We're going to look at the actual the estimated impacts of road construction on commute times, of early childhood education provision on household production time, required household production time. And we're going to put all that together to come up with the impact on time and consumption poverty for individuals and households, and see what happens. Right? So that's all tomorrow in 1 hour. We might skip a few steps just to kind of give you the broad look. Right? Okay. So questions? It was a very technical day, wasn't it?